last SOCAAR seminar. We might have one 2 weeks from now. So we're very happy to have Shunsuke Nakao here today from Clarkson University. So Shun did his PhD at University of California, Riverside. That's actually where I met him. We were in the Southern California area together doing atmospheric chemistry. He ran a lot of the chamber work studying SOA chemistry. He also did a lot of particle sizing correction methods with the DMA, with fractal particles. And then in 2012, he graduated and went to Sonia Crichton-Weiss's group and worked on CCN. And so he started at Clarkson 2 years ago. So we're happy to have him here.
Thanks for the introduction, and I really thank you for inviting. I had a wonderful day today. So today I will talk about condensation nuclear activity and volatility. Those are a couple of properties of aerosol that a lot of people study. Those properties are studied sort of as a separate quantities, but they are both molecular properties, so there has to be some relationships. So through this talk, I hope you learn something about the connection between those two quantities, and then I'll show you what we can learn from those theoretical connections between them. So as we know, aerosol is important, and organic aerosol is also important. This is a pie chart looking at submicron particles, aerosol non-refraction of submicron particle. And well, as we know, organic aerosols are everywhere, and roughly half organics, half inorganics if you limit to submicron non-refractory particles. So now I think there are a couple points important about organic aerosol. First, there are a lot of them. It's all over the world. There's a lot of them. And another thing is that it keeps changing. Now, it's not a single quantity. It changes as they age in the atmosphere. Initially, they might start life as a very low oxidized hydrocarbons like organic aerosol, and then as they get aged, this oxidation rate increase, and as they age, they get oxidized. So they keep changing. And there are a bunch of ways to represent change of organic aerosol. One successful way is to look at elemental ratio, y-axis hydrogen to carbon ratio, x-axis oxygen to carbon ratio, and then that's the equivalent plot. And we have pretty good idea where those measurement lies. Initially, it starts from the water-C ratio. Eventually, it ends up at a point here. So we have pretty good idea about those evolution. But one thing to notice that there is no information on molecule size. H2C, O2C are both normalized by number of carbons. So this representation loses information about molecule size. Another way is popular one is look at the O2C, oxidation state of carbon, y-axis, and x-axis volatility of aerosol, and that's two-dimensional volatility basically. So if you start from VOC, non-oxidized hydrocarbon, that's very volatile. O2C ratio is pretty low, and as they react, volatility decrease, O2C increase, or oxidation state decrease. So that may be your starting point, that may be your end point. And then this representation does have information about molecule size, because large particles, large molecules are generally less volatile, not depending on functional group. Another popular way is the so-called Prof diagram, y-axis oxidation state of carbon, x-axis number of carbons. So you might start from large non-oxidized hydrocarbon, and then you might end up in ultimately CO2, but atmospheric oxidation may not end up CO2, they end up somewhere around here. Again, there are many ways to represent change in organic aerosol physical property, or number of carbon, volatility, those oxidation state, and so on. And then the next question is, how about CCN activity? I think we all know that aerosol act as nuclei for clouds, so droplets. So if you want to know impact of aerosol on climate, it's useful to know change in CCN activity of organic aerosol over time as they evolve, as the physical property evolves. Yeah, here. So how about CCN? And I think many of you have seen this kind of representation, and this is a figure from one of John's paper. Y-axis is hygroscopicity parameter kappa, which I will talk about in more detail later. But anyway, higher kappa means more CCN active. X-axis O2C ratio. So as molecules get oxidized, it seems like kappa increases. 2011, a couple of years later, this paper took a little more thorough survey of available literature data. So again, there's a lot of noise, but overall, it seems like kappa increases as O2C increase. But the key point here is that so far, all of these is quite empirical. The basic approach is get as many data points as possible, try to plot in this space and see how it looks. It's all empirical. And then the question, and I like to think is there any theory behind this? You know, if you were to make some theoretical prediction, you know, how do we approach it? Can we draw any theoretical line? That's the kind of thing I want you to think about as you listen to this talk. So that's the goal or question about this talk. And then, so first of all, should kappa correlate with O2C ratio? Should CCN activity correlate with O2C? And in theory, if O2C ratio increase, that means molecules are more oxidized, more polar, polarity increase, so more polar organics, I mean, it should be more water soluble. So this makes sense. And then if higher water soluble means probably more CCN active. But well, does it really hold all the time? There are a couple of line of thoughts. Some people think it should go linear increase, and some empirical data suggest that way. For example, this paper says that, well, if you extrapolate the relationship, possibly kappa may be 0.6, that's really an upper limit, but possibly, maybe possible that the organic approaches that are inorganic or maybe ammonium sulfate. Well, just based on just drawing straight line, just based on empirical straight line. And another school of thought is that there may be some transition to less sensitive regime. This paper looked at CCN activity of very aged aerosol. And then, well, they got pretty low kappa. So there may be some upper limit on organic aerosol hygroscopicity, well, about which kappa is less sensitive to O2C ratio. So, does it keep going or does it plateau? So to answer this kind of question, I first start with some theoretical development. To those of you who work closely with CCN, this may be obvious, but I think I want to make sure everyone is on the same page. And then I will talk about some important property, solubility and density, and then finally couple it with volatility. And then lastly, I'll see what we can learn through the length of this framework. So really basic thing about CCN is, well, starts from saturation of water. Well, we know that water gets saturated at humidity 100% if you have pure water in a glass, if you have a glass of pure water. So water is saturated when RH 100%, or in other words, saturation ratio 1. And the aerosol is unique because the particle is very small, the curvature of the surface becomes significant. So and that's effective is called Kelvin effect. And this is a qualitative way to interpret this. For example, in this case, this water molecule, this guy, is surrounded by, well, four neighbors. It's an exaggerated way, but in this case, this water molecule is surrounded by, well, only three neighbors. So the number of neighboring molecules will decrease when there's significant curvature. So attraction this molecule experiences is weaker. So this water molecule right at the center is more likely to escape is condensed phase, so you will need higher saturation ratio to keep this water in equilibrium. And then that effect is some exponential dependence, and A is the slump parameter that includes surface tension of water divided by diameter of the droplet. So as you can see, smaller droplet, stronger curvature, stronger effect. And then aerosol is not a pure water. We have solution, and the effect of solution in ideal case is Prout stop, so it's called Prout effect. So a small fraction of water decrease, this saturation ratio decrease. And then this solid effect has dependence on concentration. So you see some this diameter dependence there. And then aerosol is this basically combination of both as curved surface and effect of solution. So by coupling those, well, if you take a log of saturation ratio, this A over D comes up here. Log of and small number, this small number comes up. So A over D minus B over D cubed. So A term has some surface information, surface tension information, but B term really has solid information. And so B term is initially historically used as a parameter to represent effect of solid, and that's what you find in Seinfeld textbook. More recently, people like to use parameter called kappa, but it's very closely related to this B parameter. B is good; it relates to effect of solids, but the problem with B term is that it depends on the size of the particle. It depends on the size of the amount of the solid. So B term is not really an intrinsic property. It depends on how big the particle is. It's more convenient to divide B by the dry diameter cubed. And that way we can remove the dependence of B on particle size. So kappa is purely property of solid. So again, kappa and B are both related to solid effect, but kappa purely depends on solid property. So by coupling those, so again, the exponential term is the Kelvin effect, and then Wells effect impact this water activity. And then exponential term goes up and Wells effect goes down. And by coupling those, you get this kind of curve. And when particles are small, that means solution is highly concentrated. So Wells effect wins over Kelvin effect. As droplet gets bigger and bigger, solution becomes more and more dilute. The Wells effect gets weaker, so Kelvin effect wins. So saturation ratio goes over 1. And at some point, Kelvin effect also gets weaker, so you end up having some maximum saturation ratio. So if droplet goes beyond this point, droplet can spontaneously grow, and they can activate until surrounding runs out of water vapor. So in the simplest case, let's interpret this water activity. In the simplest case, the ideal solution. In the ideal solution, water activity is nothing but mole fraction of water. Mole fraction of water, number of mole of water divided by moles of solid, moles of water, that's mole fraction. And by taking inverse of it, it's 1 plus all this quantity, it's the same thing, just flipping it. So there is a mole of solid, mole of water. As in aerosol science, we can easily measure volume of particle, not the moles of particle. So that's represented in terms of volume, and then do some unit conversion. Well, that's why we need some density and then molecular weight. So that's the simplest case. In reality, real solution is slightly more complicated because some solid can dissociate. And then not all of them dissociate completely, some only small. And then there may be some incomplete dissociation, so this osmotic coefficient accounts for those incomplete dissociation. And then usually we cannot measure each of these explicitly, so it's convenient to lump them together as one parameter, and that's kappa, again closely related to the parameter. Then this kappa can be experimentally determined based on dry particle size and then critical saturation ratio. Simple that, for example, some example values. If particle is hydrophobic, it's 0. Ammonium sulfate about 0.6, sodium chloride about 1.2. Right. So now we know what kappa is, and then the next question is how can O2C impact this? Obviously, there is no explicit dependence on O2C, so how can O2C possibly impact this? And to think about it, it's useful to get some intuitive image of kappa value. And yes, it relates to CCN activity, but there is more intuitive fundamental way to interpret this. Let's say you have some solute, let's say you have some water, and solute is there. So by definition, that's kappa. And then this form is not really easy to interpret intuitively, so I'm just rearranging this. What's in numerator? Molecular weight divided by density, which is actually molar volume of water. Right? It's always confusing, but if you divide by density, that's volume per mass, and the molecular weight, mass per mole. So it's a volume per mole unit, so it's a molar volume. Same thing for numerator. It has molar volume dimension, but you have this quantity about osmotic coefficient. So that's basically effective volume of solids. So it's not exactly molar volume. So it's more like a smaller volume that accounts for incomplete dissociation. But anyway, in the fundamental level, this kappa is simply nothing but a ratio of this molar volume of water to molar volume of solid. So if the solid is big, kappa is small. So if the solid is effectively 10 times bigger than water, kappa is just 0.1. Right? If the diameter is about 2 point something bigger, then a diameter cube maybe close to factor 10. So in this case, this solid has inherent kappa about 0.1. The volume is about 10 times bigger than water. So that's the fundamental intuitive way to interpret this. And then, well, how should kappa can possibly impact this? That brings us to the next important topic about PCN, is solubility. So, this picture implies that solid is dissolved. It's perfectly dissolved into this water. And then let's say this compound has intrinsic kappa 0.1, so it's about 10 times bigger than water. So for this case, we can draw the polar curve, Kelvin effect and Prof effect. So from this peak critical saturation ratio, we can calculate kappa for given dry diameter. So if you go through that, apparent kappa, what you can experimentally observe, should match intrinsic or inherent kappa. That's the true physical property. That's the experimentally determined value. They should match in case of soluble solid. And let's think about slightly soluble case. You might have some core of solid left, small fraction solid dissolved in water. And in that case, that's how the polar curve looks like. It may seem like a weird curve, but really you start from that dry particle, and then the particle deliquesces. So this solution is saturated. So the concentration of this solution is basically stays constant. So Raoult's effect stays constant, but as particle gets bigger and bigger, Kelvin effect goes down. So you have about same Raoult's effect, but Kelvin effect goes down. And then at this point, all the solid dissolve into water, so Raoult's effect goes down, so this whole curve gets closer to Kelvin effect. So you have some peak, and then it goes back down to 1. So in this case, if you run the experiment, apparent kappa will be based on this quantity. That's the highest saturation ratio, and then that's the dry diameter. So using this quantity, you actually end up in kappa very, very low. So very, very smaller than inherent value. And this solubility is represented by this solubility parameter, which is basically volume ratio of solid to water. Succinic acid happens to have the same solubility. So as you can see, solubility plays an important role. And solubility does impact kappa. So next question is, how does solubility depend on O2C ratio? And there is a convenient parameterization developed by Mikinori Iwata when he was at Harvard. So he took a survey of many compounds with different solubility and different O2C ratios, and he came up with this parameterization. So as O2C increase, solubility increase. So it's useful, and then in case of solubility limited regime, then we can make this logic. As O2C increase, polarity increase, water solubility increase, that means more solid, more Proust effect, and CCN activity should increase. And then this parameterization can help us that kind of interpretation. So next, let's try using this O2C parameterization for some real value. Let's say O2C ratio is 1, and then solubility parameter is 1, and let's say inherent kappa is 1, apparent kappa 0.1, then apparent kappa agree. But there is no solubility limit, so experimental determination of a critical saturation ratio works well. So next, I'm lowering the O2C ratio. You can calculate solubility limit. And then we actually start seeing some significant solubility limit. And then if I use this as the critical saturation ratio, apparent kappa is actually significantly less than less than the inherent kappa value. If I lower the O2C even further, the solubility limit increase. You see the Wells effect is pretty small. So there's not much solid dissolved in solution. And the apparent kappa is even less. Okay, so in summary, when does solubility matter? Using this parameterization, we can think about when does it matter. Solubility limitation is known to depend on particle size. So I got this number from Perez and 21. Generally, small particles are more likely to exhibit solubility limit. Large particle doesn't have much solubility limitation. And in these, for these sample different sizes, solubility limit occurs when solubility parameter is about 0.2 for 40 nanometer particle and less for larger particle. O2C, the corresponding O2C ratio for this solubility using that parameterization is about 0.8, 0.7, 0.6. So that, if I just simply interpret this, and so any organics less than O2C 0.8 with 40 nanometer particles should exhibit some solubility limit. But that seems pretty high. We also know that almost all SOA have some CCN activity, and then many of them have O2C less than 0.8. So that seems pretty high. SOA are usually CCN active, so why is that? One thing I didn't consider is the distribution of solubility. Again, here I'm using the same O2C 0.6, and then I wrote this probability distribution function for different O2C bins. Let's say everything has O2C 0.6. That's the polar curve you get. And then if I start to take some width to the distribution, actually curve changes significantly. Average is same. I'm just changing the width of the distribution. By making the distribution wider, actually this compounds in this bin start to dissolve faster. So in this condition, compounds in this bin contributes to Wells effect. And then as water increase, you start to dissolve some of this. So next Wells effect occurs there. And as you increase the width even more, the solubility limits is almost gone. And at this condition, well, apparent kappa is pretty close to inherent kappa. Okay, so again, I'm not changing the average, I'm just changing the distribution. So just a quick wrap up of solubility discussion. So average solubility does matter. And if solid, it does not dissolve, it doesn't contribute to Raoult's effect. So average solubility matter. And the higher the solubility, apparent kappa gets close to inherent kappa. It doesn't go beyond the inherent kappa, just make it close to inherent kappa. In addition to average, the distribution, the width of the distribution matters. And again, wider the distribution, well, apparent kappa closer to inherent kappa. It doesn't go over the inherent kappa. It just helps to exhibit inherent kappa. And then SOA around OC 0.6, and with reasonable distribution, the compound tends to exhibit apparent kappa closer to inherent kappa. I didn't get to this, but when SOA is internally mixed with inorganics, it's like having extremely wide solubility distribution, because inorganics are like ammonium sulfate, sodium chloride are much more soluble. So if organic SOA internally mixed with inorganics, this threshold gets even less. So about 0.3, 0.4 O2C ratio SOA should also activate without any solubility limit. So that, if we consider these points, it's actually reasonably consistent with what we see in this actual measurement. Again, going back to this simple picture, solids dissolved in water. Then in case of SOA, if O2C is about bigger than about 0.6, this pretty simple picture is actually okay. So kappa is, in principle, just depends on molar volume of water, ratio of molar volume water to smaller volume of solid. And the next question is, what can we do with this quantity, this dissociation, and then osmotic coefficient? Right, so we can predict kappa using this formula. So what if we predict this kappa value, assuming these are just 1, doesn't dissociate, and osmotic coefficient just 1. So this is a little busy slide, but y-axis prediction based on this. X-axis is measurement. So in theory, it should follow one-to-one line. And I'm showing the plot for many different compounds, carboxylic acid, some fatty acid, and so on. And it's color scale based on O2C ratio. Obviously, we see this bunch of outliers in blue, and it actually makes sense. Like this predicted value only based on molecule size. So it has nothing to do with functional group, nothing to do with O2C ratio. So just purely based on size, well, this will predict this much kappa value. But in reality, these are very low O2C. Blue are really low O2C, so they don't dissolve. So in practically, when you actually measure, there is a significant solubility limit for these guys. So this strongly deviates from 1.5. And then if you limit your target to oxidized compounds like green stuff, yellow, red, they actually follow this one-to-one line reasonably well, mostly within plus minus 30%. Okay, so actually this very simple assumption works well for O2C, high O2C compounds, highly oxidized compounds, because they are mostly water soluble. So that's the solubility, and then so we're getting closer. And then next parameter we need to think about is intensity. Right, again, that's kappa. We figured out what to do with this osmotic coefficient and aspect ratio 1. And then next thing is to think about density of solid. Right, density of solid can be actually parameterized by elemental ratio, hydrogen to carbon ratio, oxygen to carbon ratio, again developed by Mikinoe. Then I did some work, follow-up work, using a bunch of SOA data collected at UC Riverside. So this simple parameterization works well. So by plugging in this number, so kappa of organic compounds can be predicted based on H2C ratio, O2C ratio, 2C O2C, and number of carbon, right? H2C O2C. So effectively, if you know the empirical formula, you can predict kappa organics, as long as you limit your target to water soluble phase. So next step forward is to find constraints among these quantity, number of carbon, H2C, O2C. So, as long as you know these three quantity, you can calculate kappa, but these three are not a freely movable variable. They are not totally independent knobs. Molecules have to have some constraint depending on the functional group. So the next goal is to find some reasonable constraint. Again, carbon, hydrogen, oxygen, they are not really movable value. And then there has to be constraint applicable to aged organic aerosol. I got these constraints from some recent literature. One approximation is that oxygen in aged organic aerosol exists either as hydroxyl group or carbonyl. Of course, that's not perfect, but that's reasonably well. Hydroxyl group, carbonyl are the major functional group. And there is also carboxylic acid that maybe a couple that's both considered as couple of both. And then we can assume some ratio of these two moieties. In the simplest case, we can assume they are equal. Of course, not perfect, but it turns out this assumption doesn't have huge impact on it. And we can also make another assumption that double bond only exists as upon carbonyl. So that means there is no ring structure. There is no double bond equivalency to ring structure or no carbon-carbon double bond. It doesn't work for fresh aerosol, but it works okay for aged aerosol that has gone through a long time of oxidation, because the ring tends to be reactive. If you start from aromatics, they end up being some end up being ring-retaining products, but those ring-retaining products are generally pretty reactive. Ring-opening products has may have some carbon-carbon double bond, but the alkenes are very, very reactive. So as they age, those moieties get reacted away preferentially. So it's reasonable to make these assumptions. By making these assumptions, we can actually develop a constraint between hydrogen to carbon ratio, oxygen to carbon ratio, number of carbons. Right, so again, going back here, we had H2C, O2C, number of carbon, but they are not really movable quantity. Then we got to this constraint. H2C can be represented by O2C, so we basically reduce the number of variables. By using this understanding, so we can incorporate that understanding to this kappa versus O2C plot. So I posed the question, what kind of theoretical line can we draw? And then that's the answer, one answer. Right, so this kappa and O2C has some dependence, but if you limit your discussion to same carbon species, actually there's very little dependence on O2C ratio, and then there's much stronger dependence of number of carbon. Right? And then why doesn't it depend on O2C? The key here is that this kappa has both density of solid and then molecular weight of solid. Density as numerator, molecular weight as denominator. We can see that by looking at example. This one is C5, O2C 0.6, C5, O3. Right? This is molecular weight 117, estimated density 1.27. And then if you go to here, O2C doubled, so number of oxygen doubled. Molecular weight increased because you have more oxygen. but also density also increase because it's more oxygenated. So molecular weight increase, but density increase. Those increase tend to cancel out. So overall kappa end up being about the same quantity. Qualitatively, what happened is as they get oxidized, each molecule got heavier, and the molecular weight did increase. But the density also increased. When they became more polar, they started to pull each other stronger. So density increased. And those two end up in cancer. So what stronger impact is number of carbon. The same order C, you start from carbon 5, end up in carbon 10. The molecular weight increase almost doubled, or density about the same. So kappa is about half. So using that understanding, we can start to guess what kappa line, how can we draw a theoretical kappa line to this Kroll diagram. And the Kroll diagram, the y-axis of oxidation state, and then number of carbon x-axis. And similarly, oxidation state of carbon impacts kappa through limiting solubility. So we can think that beyond certain point, this oxidation state of carbon should have minor, very, very minor impact on kappa value. So if you were to draw iso kappa line, and those kappa lines should be vertical line, and it should have strong dependence of number of carbons. So that using the same formula, that's the line I can draw. Okay, so beyond certain point, solubility limit disappears. So I can start drawing line from around here. And then it's almost vertical, because the oxidation state of carbon impacts solubility, but beyond that point, it should have minor impact. And then there's stronger impact on size of the molecule or number of carbons. Right, so this is basically the first kappa line that we can draw on this Kroll diagram. Then next step is to incorporate volatility. So we can think about volatility as long as we know the size of molecule and functional group. This is a summary of volatility or saturation concentration y-axis, and then number of carbon x-axis as bunch of different type of chemicals. Now, as molecule gets bigger, it gets less volatile, so overall it decreases trend. And then as alkanes get more and more oxidized, this volatility decreases. In a simple example, we can think about this C10 or the C.4, and again making the same final assumption. We can apply this model, assuming starting 10 carbon, if you have a 4 oxygen, that's the saturation concentration you end up with. So in case of this C10 with 4 log C star about 0. But using this information, we can do a very similar thing about the kappa plot. Right, so in this kappa versus order C plot, I can overlay saturation concentration. So log C star, that's 0. So that's that's 0, that's -5. So that's 1, 2, 3. And those lines are in between. So you can see that kappa organic above 0.2 is not very likely to happen in many atmospheric cases. I mean, it can happen if you have a really, really large order C, or if you have a really, really high concentration organics that push partition to the particle phase. But in most cases, kappa beyond that point is not very atmospherically relevant. It may happen in experimental or laboratory conditions. Right. So again, I can sort of update this chart. Right. Notice that there is an approximate hygroscopicity kappa axis here. So back in 2009, that's our understanding. And as OC increase, kappa should maybe linearly increase. So that's it. understanding in 2009. Now I can update it. So it's not just straight increase, it's more like this tilted increase. So as you start from around here, and then if you end up in upper left, that'll be OA. Kappa value actually may not change. It might follow the trajectory. Kappa value will increase if you have a lot of fragmentation, and then molecule gets smaller and smaller. Kappa will increase. So by combining all of them in one figure, that's what you get. And LV OA tend to be around this range. So if aerosol is very, very aged, the kappa value may be closer to 0.1, maybe a little more, or you see a little less than 1. Okay, so for now, we know that this link does not hold beyond certain point. If the organics is solubility limited, these links hold. But once organics are fully soluble, this logic no longer holds. So instead, what drives this kappa change is the change in molar volume. Smaller molecule, higher kappa. And then, well, this also relates to saturation. Well, saturation concentration. Smaller molecule tends to be more volatile, right? So there is connection between those, and then they are all connected. So yes, O/C ratio has some impact on kappa, but not through limiting the water solubility, but through different pathways. So they are related, but not through solubility, not through polarity. So this way, we can see that those two separate physical quantities, CC and activity, and then volatility, are actually closely coupled values. I must say that there is significant error, so I did some error analysis. While looking at some representative number, kappa maybe about 0.5, and saturation, surface tension, loss ratio, and I made some representative assumption, and then I varied some plausible ranges, and then I calculate those impact on this final inferred quantity. Number of carbon, in this case, 6.78 plus minus 3.5, so it does have significant variation. C star actually has a pretty large uncertainty, so I must caution that this inferring this value is not very accurate, but it's informative at a semi-quantitative way. Finally, what can we learn from this through the lens of this framework? Isoprene SOA may be a useful system to apply this kind of process, because isoprene SOA generally is pretty high orders. Obviously, it's pretty high because the starting number of carbon is pretty small. From chamber experiments, experimentally determined kappa is about 0.16. And then from field study, a lot of people are looking at this SOA. And one of the recent literature looked at volatility of this isoprene dominated SOA in Southeast US. And what they found was that this IE-POX-derived marker, one of the significant intermediate, there's a marker related to this IE-POX. It turns out this isoprene-dominated SOA is much less volatile than what you would predict from this IE-POX structure. So there may be significant accretion products. That's what they're saying. This is the graphical abstract from the paper. So from the forest, isoprene comes out, and that's the IE-POX, and then there may be some oligomerization going on. There may be some large, less volatile accretion products. And then when they measure volatility, and they thermally dissolve those organics, and then this accretion product may be thermally decomposed and then produce C5 marker species. That's the inferred volatility, but the measured volatility is much less than inferred volatility, and then that's sort of a support experimental evidence to support that there may be significant accretion products. So that's the literature on purely looking at volatility. Let's see if we can learn anything from the viewpoint of kappa. Right, from this framework, we see that this accretion product would rise around this region. Right? So it's pretty low volatile. And then we'll see about that range. So that's where you would see accretion products. And then from chamber experiments, that's the kappa value you see. So from this framework, this number of carbon, it's about 6, or C star about 2. And then that's what you see based on volatility. So it's actually very, almost double. There's some double change. So possible interpretation is that the chamber generated SOA is pretty consistent with monomer, the size of the monomer, about 5 carbon, coming from isoprene, which is 5 carbon. Based on volatility, that suggests significant dimerization. So for both of them to happen, there may be some hydrolysis going on during droplet activation. That may be what you see in, say, for example, filter, and it may be low volatile. Once they get into CCN counter, once they activate into cloud droplet, this water might hydrolyze this dimer molecule. So then this kappa value of this will be closer to that of monomer, and then volatility will be closer to that of dimer. Possible application. So one possible application is to provide some complementary confirmation of the SIMS quantification. SIMS is great because it doesn't have much fragmentation like AMS, like electron impact, but the problem is always quantification, lack of authentic standard. The kappa provides completely different approach to the overall molecule size, so it may provide some complementary evidence about its quantification. And for this kappa, there is a lot of assumptions are made by measuring a bunch of these quantity directly. For example, kappa, H to C or C star, you can actually start to test the assumption made in this CCN calculation. For example, surface tension. That's a possible application. So just a quick summary. Kappa does relate to size of dissolved solid, and then for when order C is reasonably high, kappa doesn't depend on polarity. Polarity only matters when solubility is limited. Kappa higher than 0.2 may not be really atmospherically relevant. You really need a very, very high ether compound, so a very high Lewis ratio. Isoprene SOA may be a good system to apply this kind of thinking, and the isoprene SOA may significantly hydrolyze during droplet activation, which might have significant climate implication as well. So finally, CCN measurement provides some complementary information about volatility measurement. And volatility measurement, obviously, very challenging. You can do that with thermal denuder, but it's also, there's a lot of issue with thermal denuder measurement, so it's good to have complementary approach. Yeah, with that, I'd like to thank you for attention. That's all. Thank you.